Again, the components of energy balance are basal or resting, diet-induced thermogenesis, which is obligatory, meaning we have to do it, but this is also could be thought of as storage, say, of fat or glycogen, and facultative, which is heat production. We also have the energy expenditure of physical activity. And this isn't just exercise, although exercise is a part of it. This is spontaneous. It's the energy cost of all of our physical activities. So just moving, breathing, things, or breathing would actually be in basal. This is movement. Excess post-exercise O2 consumption. So this would be like oxygen that we consume in excess after exercise. This might also be called the activity energy expenditure. It is exercise, which doesn't have to be purposeful. And it also incorporates parts of thermogenesis, the cost of being warm-blooded. So how we maintain this is through carbohydrate oxidation, protein oxidation, and fat oxidation. Carbohydrate oxidation correlates with intake, protein oxidation correlates with intake, but fat oxidation does not correlate with intake because fat is how we store nutrients. So following an overconsumption, excess CHO, protein, and alcohol are oxidized, fat is stored. We also convert excess carbohydrates to fat, but this requires energy. So this transition requires energy. After, say, glycogen depletion from exercise, carbohydrates are preferentially stored in the muscle and less are stored in the liver. These are not oxidized. Fat, instead, is oxidized. So we can also think of total daily energy expenditure, or TEE, as resting energy expenditure plus the thermic effect of food plus activity energy expenditure. And so that activity energy expenditure is exercise, but this isn't just the exercise we think of, it's all of our body movements, and non-exercise activity, which is non-exercise activity thermogenesis, keeping our bodies warm. Thermic effect of food, resting energy expenditure. We can measure these different compartments in different ways. Doubly labeled water is our gold standard for TEE. But we cannot determine from doubly labeled water any of the individual components. Doubly labeled water can only measure the total daily energy expenditure. Now, we can get at the other aspects of energy expenditure using indirect calorimetry to measure thermic effect of feeding and resting energy expenditure. And we can measure our activity energy expenditure using indirect calorimetry, heart rate monitoring, accelerometry, GPS, pedometry, questionnaires, or observation. So how do we do this? Like I mentioned, we have direct calorimetry. I might not mention that one, but we do. Indirect calorimetry, doubly labeled water, heart rate, and accelerometry. So first, let's talk about calorimetry. Direct calorimetry measures heat. If you've taken Spanish or Latin, calor means heat measurement. This requires an insulated suit or room. We don't do direct calorimetry often. We mostly use indirect calorimetry if we're doing any sort of calorimetry. Indirect calorimetry is measuring the O2 consumed and CO2 expelled. We see these called chamber studies. This is where a person is in a room that is measuring how much oxygen is consumed and how much CO2 is expelled. They also, chambers are nice because they give a free living experience, but they tend to be small. We can get a standardized physical activity if the room has a stationary bike or a treadmill. In my lab, we have a hood, and people can lay down, have the hood on them, and we can measure how much O2 they're using and how much CO2 they're breathing out. And this usually takes around 30 minutes. A rule of thumb to remember is that 1 liter of O2 takes around 5K calories to burn. We can also then use the O2 consumed and CO2 expelled to calculate the respiratory quotient. So again, direct calorimetry, we're measuring heat. We're looking at the stored energy that gives off heat when it's completely oxidized. This is how we can measure it. Like I said, it requires an insulated room or suit, an enclosure containing a water jacket. Here, we put water through these copper coils. We have air in and air out, and we have a person doing some sort of work. And this is actually going to heat the air in the room, actually through a light bulb, and we're going to measure the amount of heat that comes off of that. The theory behind this is water passes from one end of the jacket to the other, or chamber, maintaining a constant temperature. The temperature of the water leaving the jacket is used to calculate energy expenditure. We know that a kcal is the energy required to raise 1 kilogram of water 1 degree Celsius. So the change in H2O temperature, change signified by delta, equals H2O out minus H2O in. And that temperature, we can then use this equation to see how many kcals are changed. So for instance, if the water going in is, I don't know, let's say it's 50 degrees. If the water going out is 75 degrees, how many kcals have we used? Well, 75 minus 50 is 25. And we'll say it's in Celsius. And then 25 degrees Celsius equals 1 kcal per degree Celsius. Celsius cancels out. We've used 25 kcals. If we're measuring maybe foodstuffs, we can use a bomb calorimeter. And you may have made one of these in chemistry class using a styrofoam cup. But basically, we put some food in a little cup. It's in an insulated container called the bomb. It's in a water bath, and we're measuring the temperature of the water bath. We also mix it, otherwise, it starts to get hot just around here. So we mix it so that the temperature is even. We have the oxygen that's being consumed to burn. There's some airspace and an insulator. But mostly what we're doing is setting this food on fire. Heat is coming off of it, and that heat is increasing the temperature of the water bath. So with calorimetry, we can estimate metabolic rate as kcals per day or kcals per minute using the Weir formula. And as you can see, the Weir formula is expecting indirect calorimetry because it's using oxygen consumed, VO2 expelled. The respiratory quotient is defined as CO2 eliminated, what we're breathing out, versus O2 consumed. And again, remember the equation for carbohydrates, C6H12O6. We need oxygen to oxidize it, and we get CO2 and metabolic water as our outputs. If we balance this equation, it requires 6 O2s and 6 carbon dioxides. And let's see, that gets us let's see how many oxygens we have on this side. We have 6, 18. Right now we only have 12. So we need 6 more. So we'll need 6 H2Os. So now we have 6 O2s there for a total of 18 oxygens. 18 oxygens on this side. Let's check our hydrogens. That's 12. 12. And our carbons, 6 and 6. So when we break down carbohydrates, our RQ equals 1 because the amount of oxygen consumed and the amount of CO2 produced are the same number. And 6 divided by 6 equals 1. Let me erase this really quickly, and then we can go through this example in a different way. So this actually will work for any combination of carbon, hydrogen, and oxygens, including fats. So we know we have O2 consumed and CO2 eliminated. For our glucose example again, remember this X, Y, Z match up to this X, Y, Z match up to this X and Y. So for glucose, which is C6H12O6, we can just put in 6 plus 12 divided by 4 minus 6 divided by 2. And if you do all of this math, you get 6 plus 3 minus 3. Those just cancel out. And you get 6 and 6 again. And again, 6 divided by 6 is 1. I recommend that you do this equation yourself to make sure that you understand it. So knowing that carbohydrates have a coefficient near 1, we can also estimate some proteins, which are between 8 and 9, 0.9, sorry, 0.8, 0.9. Ketones, around 0.73 if they're eucaloric. If we're in a hypocaloric state, they're around 0.66. And then different fats are around 0.7. The difference between them depends on how many carbons and oxygens and hydrogens they have. Insulin is associated with a higher RQ. This should make sense, right? Because carbohydrates require insulin to be metabolized. So a high RQ near 1 means we need insulin. Positive energy balance is also associated with higher RQ. So when we are in positive energy balance, we tend to metabolize carbohydrates first. And that's going to make our RQ, again, close to 1. A low RQ around 0.7, means that fat is being oxidized. If fat is being oxidized, it's being used as fuel. Unless we're consuming fat, it means that we're using fat stores. So let's look at this graph. On the y-axis, we have weight change in kilograms. So positive means you're gaining weight, negative means losing weight. On the x-axis, we have change in RQ between a high-fat diet and energy balance. A high-fat diet RQ should be around 0.7. Energy balance, depending on what's being consumed, should be around 1. So in this pink box, we have a low RQ change. It's negative, in fact, which means that we are using fat as fuel. This also, as you can see, the more negative the RQ is, the higher the weight change, because we're using the fat in our bodies as fuel. An RQ during a high-fat meal that is similar to an energy balance meal, if we have a high-fat meal, but our RQ is around 1, and our energy balance RQ is around 1, that means 1 minus 1 is around 0. So in the orange box, this means that even though we've had a high-fat diet, we're using carbs first, which means that fat is being stored. If fat's being stored, weight is being gained. And if we have a high IQ during a high-fat meal, so this would be like 1, and maybe this is like 0.8, who knows. But that would mean that this is a positive number, like 0.2. As you can see, there's nothing that high. It's between 0 and 0.05, but still, this means that although we ate a high-fat meal, we're still preferentially burning CHO. We're using carbs. Even if this high-fat meal had no carbohydrates, it's possible that we would still get an RQ indicating that we're using carbohydrates. Think about where we're getting them from. And you should be thinking glycogen. So low RQ in a high-fat meal, weight is probably being lost. If you have a moderate IQ, kind of mid-range, you might start to be gaining weight in this orange box. But if you have a high RQ after a high-fat meal, near 1, it means you're preferentially using CHOs or carbs. It means you're storing fat and not using fat. And overall, weight gain. So indirect calorimetry, again, the theory behind it is the oxygen needed to metabolize macronutrients and produce energy. And again, the rule of thumb, it takes around 5 kilocalories per liter per carbohydrate, and it takes a little less, around 4.6 kcals per liter. So if we don't know the RQ, we can use our 5 kcals per liter as a rule of thumb for how many calories it how many calories are required to burn 1 mole or uh, 1 liter of that. No, just 1 mole. Sorry, excuse me. If we can accurately measure O2 consumption and we know what the substrate is used, we can estimate energy expenditure. Carbohydrate. CO2 production is needed to know the substrate, though. So there are handheld calorimeters. They cover the nose and mouth, and you breathe into them. However, they are less accurate than our hood or whole room calorimeters. The gold standard, again, is doubly labeled water, but this only tells us total energy expenditure. And it needs to be assessed over a 7 to 14 day period. So like I said, it's not specific. This isn't a specific measurement. It's the total. But it is accurate. Briefly, what we do is we get a special type of water that doesn't have plain old hydrogen and oxygen. It has deuterium, which is similar to hydrogen, but has, I believe it has a neutron, and oxygen 18, which has, let's see, oxygen has 6 protons, so it has 12 neutrons. And it's administered orally via water. We then also have to collect urine samples, and we measure the rate of elimination of the deuterium and the oxygen 18, and that is equivalent to the rate of carbon dioxide production. From there, we can convert it to a total daily energy expenditure. But again, we cannot get resting energy expenditure or exercise energy expenditure from doubly labeled water. Only total energy expenditure. Here's another way of looking at it. We give a dose of deuterium and oxygen 18 labeled H2O. The body metabolizes food and water. It changes that from body water to CHO, and eventually we're going to pee out the deuterium and the carbon dioxide and the oxygen 18, and then we can measure that rate and we can solve for CO2. A more indirect way is using a heart rate monitor, and this is based on an assumption of a linear relationship between heart rate and oxygen consumption. So this means that it would look like this. O2 used, heart rate. Actually, sorry, it makes more sense if we do it this way. Oops, no, come on, give me my little, there we go. Heart rate, oxygen consumed. We're assuming the relationship looks like this. But it's more variable at the low range and high range. So this is the best practice to estimate O2 and CO2 consumption. I'm not going to go through it, but please read it. And this is specific to cycling or running. So this won't be valid for something like weightlifting. And like I said, it's less accurate at low intensities, but it can be compensated for with fancy modeling. So again, heart rate we assume is linearly related to oxygen consumption. And we would then fit a slope. But this is influenced by the temperature, the type of exercise, if the person's dehydrated, or overtraining. If they're overtraining, they have less glycogen. Heart rate monitors are able to quantify the intensity and estimate the energy expenditure of aerobic activity. Again, running or cycling. And it is described to either heart rate reserve or percent heart rate max. Accelerometers, on the other hand, measure how much we're changing in different directions. And all monitors are different, and they have to be validated. It also depends on the location where they're worn. Say, hip locations may not pick up static motion, like moving your arms or cycling. The trunk is the standard. Wrist and ankle should be avoided because there's a lot of excess motion in the wrist and ankle. Think about when people were trying to get their steps in when they were wearing Fitbits and they were just moving their arms around. And more is better. Multiple monitors in, say, the hip, trunk, and wrist is better. And it's better to get more days. 3 to 5 for adults and 9 to 11 for children. Our current methods to estimate energy expenditure, again, are linear. And linear equations tend to under or overestimate based on the locomotion pattern. But we can personalize the calibration. But standards in this field are still lacking. So resting energy expenditure. Like I mentioned before, resting expenditure is linearly related to fat and fat-free mass. But most importantly, as body size. So we see that even though an obese person may have more fat mass, they're still going to have a higher energy expenditure than a lean person. But that is primarily due to this physical activity aspect. It takes a lot of energy to move around a larger body, even though fat-free mass is more metabolically active compared to fat mass. Metabolically active, keep in mind, means that ATP is being used. Fat mass and fat-free mass only account for around 70% of total resting energy expenditure. And that's because a large part is from our vital organs. Our brains especially use a ton of energy. And so this line is just demonstrating that even though this person is obese, their resting energy is still this much, which, let's see, I'm trying to see how much that is. It's hard to draw a nice straight line. But it's a good amount higher than the lean person, which is here. So this is a picture of indirect calorimetry using a hood. This is a picture of one in a hospital. I don't know why there was a noise for that. That's weird. But the factors that influence REE are body size, body composition, and sex. And the sex also plays body composition. Gonna have to look where that noise is. That's weird. Age also. So we know that as we age, REE tends to decline. Also, think about infants. Infants are resting energy expenditure machines. They are giving off a lot. Other aspects are genetics and body temperature. If you're running a fever, your resting energy expenditure is going to be high. Let me clear, whoops. Also, things like menstrual cycle phase, which also influence body temperature, and hormones, as well as fasting or severe dieting, will impact resting energy expenditure, along with overeating, exercise training, acute exercise, smoking, caffeine, extreme temperatures, and illness. So, how we can estimate resting metabolic rates are using a couple of equations. The Cunningham equation requires us to know lean body weight. We take that, multiply it by 22, add 500. The WHO, or World Health Organization, uses total body weight, and it has a male and a female equation. And the one we use quite often is the Harris-Benedict. We use that for, say, how many kcals we need to eat per day. But there's also, as you're familiar with, Mifflin St. George. There's also the organ tissue model, and this accounts for around 80% of variation. But it lacks an account of metabolic variation. Think about how are these systems different in individuals with excess adipose tissue? Think about gluconeogenesis, de novo lipogenesis, and protein turnover. But what the organ tissue model is really looking at is how much different organ systems like adipose tissue, circulatory, endocrine, musculoskeletal, how much each of these tissues, how much energy they use.